Good morning, afternoon, or evening. How y'all doing today? Welcome back to Morrow's Math Corner. Today we're going to be learning about functions involving radicals. So let's get right to it. Let's first remember that you can evaluate any function by simply plugging in the x value, which is the independent variable, into the function and solving for the y value or values, which is the dependent variable. So for this example, I'm given f of x and g of x. Please remember that when we read f of x, this is simply saying this is function f with independent variable x. And g of x is function g with independent variable x. So when I'm asked to evaluate f of 7, I'm simply replacing every x in function f with the number 7. So I've got the square root of 7 plus 2, which equals the square root of 9. Square root of 9 equals 3. So that means that f of 7 equals 3. How do I translate that? That means that when x is 7, y is 3. For g of negative 3, remember that I'm replacing every x in function g with a negative 3. So I've got the cube root of 3 times negative 3 plus 1. That's the cube root of negative 9 plus 1, which equals the cube root of negative 8. So g of negative 3 equals the cube root of negative 8, which is negative 2. So that means that when x is negative 3, my y value is negative 2. And another example here, f of 10. Please remember that we're simply replacing the x in function f with a 10. So this is the square root of 10 plus 2, which equals the square root of 12. We can break down this 12 into 3 times 4. Remember that the square root of 4 is 2. So f of 10 equals 2 times the square root of 3. Just in case you forgot how I got that 2, remember that 4 breaks down into a 2 and a 2, and every pair comes out as one of that value. So what we're dealing with here is the fact that when x is 10, y is 2 square root of 3. And that's how easy evaluating radicals are. When we're talking about domains of radical functions, there's two types. Ones with even roots and ones with odd roots. If the root or the index of the radical is even, and in the numerator, then the radicand must be set greater than or equal to 0 and solved. This will give you the valid x values for the domain. Therefore, the domain is every number within the defined parameters. If the root or index of the radical is odd, then the domain is all real numbers, since odd roots can be negative or positive. There are no limitations, there are no restrictions for odd indexed radicals. So let's find the domain of each of the following in example 2. For 2a here, we have f of x is equal to the square root of x minus 5. Please remember that there's an even 2 here as an index. It's just invisible. So that means that this is even, so therefore the radicand, the inside part of the radical, must be set to greater than or equal to 0. So I'm going to add 5 to both sides. X is therefore greater than or equal to 5. So my domain is from positive 5 to positive infinity. Anything greater than or equal to 5 will be a valid x value, and therefore I can plug those into the function and find the corresponding valid y values. For b, I've got g of x equals the cube root of 2x plus 1. Since 3 is an odd index, the domain is automatically all real numbers from negative infinity to positive infinity. There are no restrictions. H of t is equal to the fourth root of 5 minus 2t. Since 4 is even, I must go ahead and set my radicand, or the inside part of the radical, to greater than or equal to 0. I'm going to subtract 5 to both sides. 2t is greater than or equal to negative 5. I'm going to divide by negative 2. And please remember that when you're dividing by a negative, you must flip the inequality. So now I've got t is less than or equal to 5 halves. So that means that the domain is going from negative infinity to 5 halves with a bracket because 5 halves is included. For graphing functions involving square roots, let's first remember that the domain of the parent function, which is f of x equals square root of x, is x is greater than or equal to 0. And if we graph the parent function, when x is 0 and you plug it in, y is 0. When x is 1, y is 1. When x is 4, y is 2. And this is your parent function of a square root. Okay? Now, what happens when I alter that? You have two options. Let's say I want to graph f of x is equal to the square root of x minus 2. Option 1, first find the domain of the function, then make a table of values using the valid x values. Then plot the ordered pairs and graph according to the pattern of the square root function. So let's go ahead and first find the domain. Since this is a square root, it's even, I've got to set x minus 2 greater than or equal to 0. I add 2 to both sides. X is greater than or equal to 2. So therefore, the domain is from 2 to infinity. So I can choose x values that are 2 or larger. Now I'm going to choose strategic values that are going to render me with a perfect square. So when x is 2, remember you got 2 minus 2, which is the square root of 0, which is 0. When x is 3, 3 minus 2 is the square root of 1, which is 1. When x is 6, 6 minus 2 is the square root of 4, which equals 2. I'm always going to do my best to choose x values that are going to render me with a perfect square. So I go ahead and now graph these points. So I've got 2, 0. I've got 1, 2, 3, 1. And I've got 1, 2, 3, 4, 5, 6, 2. And that is my function, graphed and perfect. And if you notice, it is following the fact that the x values are from 2 to infinity. Okay, what's the second option? Well, option 2 here is to first graph the parent function, f of x equals the square root of x. Then shift each point according to f of x equals a times square root of x minus h plus k, where h is the horizontal shift. Notice that it's x minus h, so it's opposite of what's given. And k is a vertical shift. You don't have to go opposite there. It's exactly verbatim as what they give you. So first, my parent. When x is 0, y is 0. When x is 1, y is 1. When x is 4, y is 2. And I have my 0, 0, 1, 1, 4, 2, and that's my parent. Now, let's go ahead and shift. If you notice here, I've got an h. This is x minus 2. So that means that my h is actually positive 2. It's opposite of what's given. So I'm going to literally shift each of these 2 to the right. So this 0, 0 goes 1, 2 to the right. This 1, 1 goes 1, 2 to the right. This 4, 2 goes 1, 2 to the right. And that would be my function. So it really depends on what you like best. You can either do option 1 or 2, whatever works best for you. Let's say I want to graph a function involving cubic roots. Well, once again, let's remember that the domain of the parent cube root function of f of x equals cube root of x is negative infinity to positive infinity. There are no restrictions here. When x is negative 1, wait a second, how can I have a negative? Because it's an odd index. So you can have a radicand that's positive or negative. The cube root of negative 1 is negative 1. The cube root of 0 is 0. And the cube root of 1 is 1. And the cube root has this weird kind of S shape. It's not really an S, but it's kind of like an S shape function. So now we want to go ahead and graph this, but with shifting, okay? We want to graph something other than the parent cubic function. So option 1, very similar to square root option 1. First find the domain, then make a table of values using valid x values, plot the ordered pairs, and graph according to the pattern of the square root function. I'm always going to try to use values that are perfect squares, perfect cubes. So my domain here is just negative infinity to positive infinity. And I'm going to use x values that are perfect cubes. So the cube root of negative 1 is negative 1 plus 2. We've got negative 1 plus 2 is 1. The cube root of 0 is 0 plus 2 is 2. The cube root of 1 is 1 plus 2 is 3. So I've got my points here. Sorry about that. So I've got my points here. Negative 1, 1, 0, 2, and 1, 1, 2, 3. And do the best that you can here. This is going to be kind of a funky S value here. Okay. Option 2, very similar to option 2 for square roots. Graph the parent function of f of x equals the cube root of x and shift each point according to f of x equals a times the cube root of x minus h plus k, where h, once again, is the horizontal shift, and it's always opposite of the given h, and k is the vertical shift. So we're going to go ahead and first graph the parent function here. When x is negative 1, y is negative 1. When x is 0, y is 0. When x is 1, y is 1. So that is my parent function here for the cube root. And now we're going to shift. Now in this particular example, we don't have an h, but we do have a k. So that means I'm going to literally shift every single one of these points vertically up 2. So this is going to go up 1, 2. This 0, 0 is going to go up 1, 2. And this 1, 1 is going to go up 1, 2. And I'm going to do the best that I can to have this S-shaped kind of function. And there you have it. It's that simple. Hope you learned a lot. Thanks for watching. Come back anytime. Take care now. Bye-bye.